over again. So again, welcome everyone to the November session for the online viewing sessions. My name is Richard Bell, and I'll be your host for the evening. And so we're going to take a tour of the kind of late summer and early autumn sky with our telescope in Arizona. And it sounds like we're getting there. So let me kill some time here. Let me introduce you to the remote telescope while we're waiting for it to get dark, because again, that daylight saving time is wreaking havoc on us. And I got a million things going on at once here, so that's why I sound a little distracted. But I think we're good. Okay, so you should be seeing the title slide there again. And so this is actually a panorama on the title slide there that a local resident took for us named Rick Benno. This is actually his place right there. So we have Rick Benno on the left and his observatory called Conferring with the Sky. And over here is the residence of KAS member Mike Patton, or I should say the winter residence. He's not quite there yet, but he'll be back out there again soon. So this is his home, and this is where our telescope is in this observatory right here. And between the two, you can, of course, see more observatories and more houses. But this right here is Cave Creek Canyon, which is located at a place called Arizona Sky Village. So here, of course, is a map of the state of Arizona. And you can see that little red star down there. And that is the approximate location of Arizona Sky Village. The nearest town, if you want to call it that, is called Portal, Arizona. It's a really small hamlet. It's unincorporated, and but it's a really, really great place. So really quick here, because this will not take long, let me give you a tour of downtown Portal, Arizona. Here's the post office. So you can see it's zip code 85632. So you can possibly pick up your mail there. The last I knew from Mike Patton is the kind of the mail person there is like pushing 90. So sometimes people come pick up their mail, but there are some people that make or, deliver the mail, which seems kind of unconscionable to me. So there's the local post office. And here is the Portal Store, Cafe, and Lounge. And this concludes our tour of Portal, Arizona. So that's pretty much it. You don't want any more than that. And so it is a small place. And as you can see here from this light pollution map from Google Earth, it is dark. So we have Arizona Sky Village here. They don't even show Portal on this scale. If you want to go get groceries at Arizona Sky Village, you take like the 2-hour drive down to Douglas. So you don't really get quite a sense of scale here. So, this is like roughly 2 hours away down the Douglas, which is right on the Arizona-Mexico border. And of course, you can see Sierra Vista. There's some smaller towns here. And way off to the left of the screen is Tucson. So it is a very dark area, and it's in the Coronado National Forest. So national forest land around here cannot be developed. So it'll stay dark for quite some time. So that's why Mike Patton moved there. And that's why we decided to put the telescope there after an offer by him. So here's another light pollution map with the Bortle scale on the left. And again, the X denotes where Arizona Sky Village. And here, Douglas looks really close. But again, that's like 2 hours away. So you see Tucson, like over 3 hours off to the west here. Phoenix is even further off to the northwest. So we really don't get any effects of light pollution from Tucson or Phoenix, but we do get some light pollution from some of the really local sources here, not even El Paso. And so on the Bortle scale, Arizona Sky Village ranks about an upper level 2, not quite the bottom of the 2 here where it's more gray, it's closer to black here. We're not quite 1 because of the light pollution nearby, if you can even call it that. what we think of light pollution. It's not really light pollution there. It's just little light domes. So it is really, really dark there. If you have excellent eyesight on a really clear night with no moon, you can see to about 7.5 magnitude. So here is Mike Patton. I'm not sure if Mike registered to join us. I'm not sure if he's here. He can chime in if he wants to. But way back in January of 2008, Mike Patton here walked up to me at one of our general meetings and said, hey, Richard, I'm building a house and observatory at Arizona Sky Village. And I'm like, hey, that's great, Mike, wondering why he's telling me this, because I didn't care because I was jealous. And he basically said, hey, I'll need technical guidance and advice from time to time. And in exchange for that, I'll let you guys have one corner of my observatory for a remotely controlled telescope. And of course, I was like, absolutely, let's do it. But it wasn't entirely up to me. So, some time went by before we finally accepted it and decided to pursue the project. So here is the observatory under construction. You can see this is November 2009. And we see 4 pads here for the roll-off structure that'll support the roof when it's rolled off. And this is the floor of the roof. And our remote telescope will be on this spot right here. Okay. And then you can see the observatory taking shape here. At first, he wasn't going to build a warm room, which they also sometimes call a cool room out there because it can get pretty hot during the day. But I kind of talked him into that. So we do have a warm room, and our computer that controls the telescope sits right here. And of course, our telescope is just on the other side of this window here, or at least it will be. And you can see the observatory taking shape here. So it actually looks like an observatory now. It has the roll-off, the pylons here for the roll-off roof to support the weight. And, it just looks like your typical roll-off roof observatory. It's a 20 by 20 structure, and you just got to basically add some trimmings here and some siding. So I didn't get out there in person to check the place out until October of 2010, when basically the building was complete. Unfortunately, the roof shifted a bit or settled a bit, and he couldn't roll it off while I was there. But I did get to check the site out, and he picked up, he wanted his main telescope over in the corner over here. And but I really wanted the telescope here anyway. I wanted to have it close to the computer. And this is the north wall here. So we have kind of a little better view of the south. He's a little crammed to the south wall there. So frankly, I think we got the best spot in the observatory. So some time went in here, but I picked the site, and then we did the fundraiser, and then it was basically 1,915 days until we filled that empty corner. But again, between that time, between October 2010 and December 29th, 2015, we had to do some fundraising. And the good news is we already had a pretty good head start, because we were already doing some fundraising and sales to purchase a piece of dark sky property. And the fundraiser officially began around 2010 or so. And so really around 2010, you can see the fundraising levels skyrocket here. So we're really proud of this. This is the largest fundraiser in our organization's history, even larger than the fundraiser that our group did in the late 50s to bring the first planetarium to Kalamazoo, because we did that. And we raised, as you can see at the very end here, about $122,000, which is incredibly impressive for a modest size group like ours. And we're pleased to announce that, or mention that roughly 60% of those donations, 60% of that $122,000 that we raised is from Kalamazoo Astronomical Society members. And we did get, some grants. I did write some grants, and that constitutes about 31% of the total. And you can see we did get some public donations, but we probably didn't pursue it as much as we needed to. If we really needed to, we probably would have done a bit more. And we did do sales. We had telescopes donated. We sold eclipse shades for the Venus transit in 2012. So we did do some sales. And we even got 1% from bank interest because, the fundraiser lasted for over 7 years. So during that time, we accumulated just a minute amount of interest. So here is the observatory today. This picture was taken just this past March, I believe. And this shows the observatory, which is now called Peishi Observatory.
Bring them up on my
Mike Patton
to listen to them on.
We can hear you, please. Please mute yourself, John. Thank you. Remember, we are on Zoom. If you talk, anybody can hear you. So here is Peishi Observatory, and Mike Patton wanted to keep an owl, a bird theme, because we have an observatory here in Kalamazoo called Owl Observatory, and so Mike wanted to have a name that kind of went along with the bird theme. So Peishi in local Apache, I think it is, means nighthawk. So in English, it's Nighthawk Observatory. And but of course we call it Peishi, and we're pretty sure we are pronouncing that correctly. We never to get confirmation of that, but one day I hope to speak to an Apache and get it for sure. So it is a roll-off roof observatory that has 4 telescopes inside. One's a solar telescope. The other 2, the solar telescope belongs to Mike, and the other 2 belong to Mike. He has like a 14-inch Meade Schmidt Cassegrain on a plane wave mount, and he has a 7-inch Meade refractor on a plane wave mount now. And then the other telescope in there is ours, and you can see it poking up here. So it is a 20 by 20 roll-off roof observatory. So it does measure 20 by 20. So there is plenty of room to move around inside, but aside from Mike, hardly anyone's ever there. You know, we use it remotely. You know, we've only been there a handful of times. And you can see on the back here is the weather station. The last I checked, the wind was getting higher and higher, which it wasn't supposed to tonight. The winds were supposed to be quite calm, but they always seem to increase a bit after sunset and then maybe die down for a while. I'd say maybe, because they don't always do that. And you see this little structure here, which I'll show you a close-up picture of. So this is our SBIG All-Sky-340C camera. It is no longer produced, but it is a great camera for us. So let me move to a different screen here. I think I have the proper screen up. And we'll switch screens here, and we'll see how the skies are doing out there. But I want to have the right screen up here, so I had to switch around. Okay, there we go. Now I can see it. I think that's the right one. Okay, so things are looking much better now. So this is the live view from our all-sky camera. And you can, of course, see the horizon around you. This gives a fisheye view. And we have this little funky structure here in the south. So yeah, south is at the bottom, north is at the top. East is over here and west is over here. So west is on the right, east is on the left. So it's kind of backwards, which makes sense because we're looking up in the sky. And so this little funky structure here is a bird perch, because we had a bit of a trouble at first. You know, birds apparently like to land at the highest point, which was the dome of the all-sky camera. And they would often, you know, for lack of a better word, poop on the dome. So to help cut that down, we installed this perch here, and so far it seems to have worked. You know, occasionally we'll catch a bird on the dome, but normally we find them on the perch. So that has worked and kept birds off the all-sky camera. And up in the upper right here, you can see Mike Patton's house that I had in the opening slide there. And you can't quite make it out, but Rick Benno's place is over here, the Conferring with the Sky Observatory. He does have a website, so later on you can Google Conferring with the Sky Observatory. And you can see some really bright objects over here in the southwest. We have the planet Venus. And just above kind of the pointing here from the bird perch is Saturn. And over here is Jupiter. So we do have 3 planets currently visible. People often ask if they can see the planets with the remote telescope, but they are not really equipped to do the planets. Even the big scope, the 20-inch, doesn't have sufficient focal length to really zoom in and show you details on the planets. We built the remote telescope for deep sky use. And of course, the cameras are really sensitive to cool them so they're not so noisy and pick up the faint light much better. So they really overexpose the planets. We did do images of Jupiter and Saturn when they were really close together at the end of 2019. But even then, you really couldn't see any details on the planets. So we really can't do the planets. And you can also see, of course, the Milky Way through the picture. And right now, Venus is like right in the heart of the Milky Way. So right here, it's still a little hard to see because you can see it's not quite fully dark yet, but it should be getting there. It should be fully dark about now. And we have Venus right in the heart of the Milky Way, right in the central bulge of the Milky Way. So the center of our galaxy is like 28,000 light years in this direction. And we can see one arm of our galaxy sweep across the sky here. And we do have several constellations visible. I'll point out an asterism first. We have the summer triangle. We have Vega, Deneb, and Altair. So there is the summer triangle. And we will look at some targets in Cygnus here later. We'll look at a target right here. In fact, you can see it like right there. And we'll look at a target like down here. So we will focus on Cygnus a bit, which is technically a summer constellation, but that's okay. Oh, and you just saw it reload there because our all-sky camera takes a new picture every 4 minutes. So I have the web page here reload every 4 minutes. Unfortunately, they're very rarely ever in sync, but it kind of works. So another asterism is the Great Square. We have the Great Square over here. So these 3 stars belong to Pegasus. So this is the back of Pegasus. You can see the head here, and there's like a leg, a straight leg here, and kind of a bent leg here. And then we have Alpheratz, which is the head of Andromeda, which kind of arcs off this way and this way. And basically right behind the spot, right behind the spot right there, because again, it's been a while since Mike Patton's been out there to clean the dome for us, is the Andromeda Galaxy. So once he gets out there and cleans the dome, we would be able to see Andromeda in this position again. But we will take a close-up look at Andromeda as well tonight. That's one of the targets that we do all the time. And you can see an airplane here. We have caught the occasional meteor, but it's not really a meteor cam per se, but we have picked up some faint meteors. I've never seen anything really spectacular. And one more summer constellation, we do have Sagittarius down here. We have the teapot. You can see the handle of the teapot and the spout. And here's the top. And of course, rising from the spout is steam, which is the Milky Way. And we do have the constellation Capricornus. Right now, both Saturn and Jupiter are in Capricornus, which kind of looks like a Cheshire cat smile. Kind of has that wedge shape to it. And over here, kind of going from here to over here is Aquarius. And a whole lot more. You can also see, I'll point out one more here. I'll point out Cassiopeia. And you can just now see the Pleiades emerge. And of course, right now you can't really see the Big Dipper or Ursa Major at all. But right here, I think is Polaris. But we lose the northern part with the camera here. That's by design. And so we won't be able to see Ursa Major until it rises later in the season. Okay, so that's the all-sky camera, and we will go back here from time to time, but of course you can go to the address here, and perhaps while we're taking a tour with the telescopes, if you happen to see like a bright meteor or something, let me know, and we'll switch back to the all-sky camera, and we can check it out together. All right, so our very first target tonight, or our very first targets tonight, I should say, will be with the Takahashi Telescope. So I'll give you a second here to read this information. And while you're doing that, because again, I'm doing this solo, I'm going to enter in our very first target. So give me just a second here, and I'll see if I can get this going, and we'll tell you a little bit about the Takahashi. So normally it's really easy to go to the first target here, but I want it to center this target in a very specific way. So I have to enter in some custom coordinates here. So it'll take a little bit longer than usual, but not too much longer. So I'm one of those people that can't walk and chew gum at the same time. Okay. All right, we should be good there. All right, so hopefully you had some time to check out our Takahashi. So yes, this is 1/2 of the remote telescope. So we often start with the Takahashi here. I know many people are anxious to see stuff with the big telescope, but you'll see the smaller telescope can do some amazing things. This scope can show us things. Of course, the bigger scope can't because the Takahashi has a considerably wider field of view. And we do have identical cameras on both telescopes. So the camera that we use on both scopes is the old SBIG STX 16803 camera, which is a full frame camera. The chip is nearly 37 millimeters square. And you can see it has about a 17 megapixel resolution, which is, getting low by today's standards. But out in Arizona, we only have DSL. So the internet out there is painfully slow compared to what we're used to today. So I don't think I want like a 40, 50 megapixel camera out there just yet, because it would take a long time to upload the images to our cloud account, because that's where all the members get their images from. It's from our Google cloud account. So we again use the same camera and actually the exact same filters on both telescopes. We have a 7 filter wheel on both telescopes. And the telescope should be currently slewing. So let's see if I can find, there we go. So the telescope is moved. And you can see, of course, the little flip flap for the Takahashi is open. And pretty soon here, what'll happen is it'll do some plate solving for exact centering. So the target will be exactly centered as I wanted on the chip. And then it'll look for a guide star. And then hopefully it'll start guiding, because it should find a guide star, because we were looking like right in the Milky Way. So that should not be a problem. And then it'll start taking the exposure. So you can see I'm using the Edge browser, because other browsers don't tend to work very well for our live PEC cam here, because it tends to freeze. So it runs really well on Edge. And again, you can view this right now or at any time on your own, but you might have to change some settings in your browser. And we do have instructions down below on the webpage here to how to change your browser so you can view this or allow it to view the stream here. And I can hear the camera look for a guide star. So it's ringing in my ear, which is kind of annoying, but that's okay. So it sounds like it's going to guide here pretty soon. And so we'll check on the telescope from time to time, because I missed it slewing this time, but hopefully we'll get it in motion here later. So allow me to introduce our very first target of the evening. Here's where we're going to start looking. So as promised, we're going to look in the constellation Cygnus here. So again, you can see Cygnus This is like the neck and head of the swan here. This is her tail. There's a wing here that goes out to these three faint stars, and there's a wing here. And you can again see Deneb, one corner of the summer triangle. We have Vega down here and Altair here. So we're looking kind of just outside the summer triangle toward, I think, oh gosh, what is it? The eastern edge? Yeah, the eastern edge of the triangle. And we'll zoom in here for a closer target. And you can see we actually have multiple targets planned. So we have multiple NGC objects like 69, 6960, 6992, 6995, and so on. There's even more than what's shown here. So this gives you a closer view of our next target here, which you can see is called the Veil Nebula. That's one name for it. But many of us call the entire thing the Cygnus loop. But there are two halves to this object, or at least two popular halves. And we're going to look at both of them together. So we will look at NGC 6992/6995. I think the bottom part where you can see there's kind of like a separation here. This is 6995. The bulk of it here is 6992. And I always try to show a sketch from an amateur. I try to give credit if I can find the artist, but in this case I couldn't. And so this is the view through a telescope of unknown size, but it looks pretty bright here. So it's probably a good size Dobb or Schmidt-Cassegrain or something. And most people tend to refer to this half of the Cygnus loop as, not just the Veil Nebula, but the Eastern Veil Nebula. Because there is a Western Veil Nebula, which is NGC 6960, but I call it the Witch's Broom. I've always preferred that name better, but it does go by multiple names. Of course, the Cygnus loop is best known as the Veil Nebula, but some sources have called it the Cirrus Nebula or the Filamentary Nebula. And again, the several other components have names as well, as I'll point out. And so backing up here, we'll back up just a bit here because I think I jumped ahead. NGC 6992 and 6995, which is the Eastern Veil Nebula, is about 3 degrees southeast of Epsilon Cygni and 4 degrees west of Zeta Cygni. Okay.
For death, I'm living with.
All right, so we'll keep muting people there. So only unmute yourself if you actually have a question for me. We don't need to hear your background noise there. So these are located 3 degrees southeast of Epsilon Cygni and 4 degrees west of Zeta Cygni, while the other half, the Western Veil Nebula, is located 3 degrees south of Epsilon Cygni, and it's kind of superimposed, as you can see, with 52 Cygni here. There it is right there, which is quite brilliant when you're looking at it, when you're trying to see this faint object through a telescope. Now, some parts were discovered by William Herschel on September 5th and probably September 7th, 1784. And so we're pretty certain that William Herschel discovered 6960, 6992, and 6979. So he didn't discover the entire thing because some parts are rather faint and they're actually easier to see, with a big telescope or through images. So we'll skip past these again. And basically what we're going to see here is a supernova remnant. But in some ways it's not exactly the supernova remnant itself, but I'll explain that later. So this we know is a type 2 supernova, also known as a core collapse supernova. So you might know that all stars at one time or another in their core fuse hydrogen into helium, and they spend a long time doing this. And eventually the hydrogen in the core will be gone, and eventually the core will begin to fuse helium. But the core may eventually fuse helium, but before that, an outer shell will begin to fuse hydrogen into helium, just like it did in the core. And then eventually, for example, the helium in the core will be gone for massive stars and for stars like the sun, but the big difference is the sun can't fuse the carbon made in the helium fusion process, because again, hydrogen makes helium, helium makes carbon, but the sun can't fuse carbon into still heavier elements, but big stars can. So it'll eventually fuse carbon in the core, and then it'll have like a helium shell above that, and then the hydrogen shell above that, and so on and so forth. Eventually, it'll begin burning other elements in the core until we get down to iron fusion, which doesn't last very long at all. So you can see here, we're at the very end. We have iron fusion in the core, which says no fusion, but it's not fusion that releases energy. It's fusion that absorbs energy, which is bad, as we'll see. And then we have a silicon shell above that, oxygen shell above that, and so on. So these stars can develop very complex structures as they begin to die. And so I'm not really sure we know the mass that this star had before it blew up, before the Cygnus loop star blew up and created what we call the Cygnus loop or the Veil Nebula today. But here, for example, is a 25 solar mass star. So 25 times the mass of the sun. And again, you can see the hydrogen and the helium stage lasted for 7 million years. While in the sun, it'll last about 10 billion years. But in either case, it's 90% of the star's lifetime. So stars spend approximately 90% of their lifetime fusing hydrogen into helium in their core. But each stage goes faster and faster. So you can see helium fusion into carbon and oxygen is way shorter than it was for hydrogen, because number one, there's less helium in the core than there was for hydrogen, so there's less gas in the tank. And also helium fusion is less efficient than hydrogen fusion. And so if it's less efficient, that means it has to burn faster to fight off gravity, because that's what this fusion process is even for, is to fight off the crushing force of gravity. And then eventually, each stage goes faster and faster. Then we get down to silicon fusion into iron, which lasts a day. And then when we get to iron fusion, that lasts about 1/10 of a second. And then suddenly the iron core collapses, and then the outer layers implode and rebound like this in a supernova explosion. And so what we're going to view is kind of the remnants, per se, of this explosion sometime in the past. So the really cool thing about supernovae like this is that's where the bulk of the elements that we are made up of come from. All the hydrogen came from the Big Bang. Most of the helium came from the Big Bang, but not all of it. And you can see pretty much everything else, is denoted below, is from some type of dying star. So like the iron in our blood, the oxygen we breathe and so on, came from dead stars. Okay, so let me go back to the screen, the web browser here. And we'll see how we're doing here. So, we're doing really great. So we're almost done here. And this program here is called ACP, for the Astronomer's Control Panel. And this is basically a program that controls other programs. So any member that has access to the remote telescope uses it through ACP here. But you basically connect to the computer that we have out west. And I'll show you the computer screen out west here later, but we're almost done here. And so we got about 40 seconds left. So while we're waiting, you should be able to unmute yourself. So if anyone has any quick questions, I'm happy to take them. Or if anyone wants to make any comments or anything, now's the time to unmute yourself and say hello.
No questions, but I'm really happy to be back.
Well, thank you, Kathy. It's good to hear from you. Oh, we're almost done. For some reason, it always goes like 2 seconds or more over. I really don't know why. The actual picture isn't over. And you can see we're using the hydrogen alpha filter, because that is the best way to pick this up and not have the stars blown up. Because if we do it with the clear filter, boy, is it bright. The stars are really bright. So there it is. All right, so we can see it, but we'll give it a second to load. The thumbnail loads first, and then the actual image has to load next. So there's a bit of processing going on in the background here. Oh, you know what? I forgot to change the focal length for the Takahashi. That's why it's not quite centered. Well, we'll see how we're doing here. Usually I hear a little dong, but well, let's see what's going on with the computer out there. It looks like it's done. Oh, it's trying to plate solve. So it's not happy. It's, before we do anything, I'll change the focal length next, but there we go. All right, so now it's complete. So I got to remember to switch that. And there we go. Everybody see that?
Yeah, that's amazing.
Okay. Oh, gotta let somebody else in here. Okay. So let me tell you a little bit about this here, and I'll give you some time to look at it. Looks like we did catch a satellite. I have no idea which one. But again, as mentioned, what you're looking at here is sort of the remains of a type 2 supernova that, according to a more recent source that I looked at, occurred about 5,000 years ago. One source that I had written down went back further than that, roughly 12,000 years, but you know, who knows, you know, so I would say this supernova occurred at least 5,000 years ago. And the entire thing here, from one side to the other, is about 130 light years across, which at its distance works out to be about 3 degrees in size, you know, 3 degrees in angular diameter. That's 6 times the diameter, or 36 times the area of the full moon. So this whole thing here is like 6 full moons, but you could fit like 36 moons inside. So in the sky, it's really big. But of course, it's far away and it's faint and we can't see it. Now, I mentioned, you know, most sources would call the Veil Nebula here, or the Cygnus loop. You know, the whole thing is called the Cygnus loop. But you know, when these stars go supernova, they create a massive explosion. They do have debris that expands outward, but according to one source, this could be basically just material in the interstellar medium that's getting compressed by the shock wave from the supernova. I still always kind of think that it's a supernova remnant. That's what pretty much every source calls about it. But, you know, a more recent source says this is from the shock wave compressing the gas in the interstellar medium.
Got a question, please.
Yes, go ahead, Joe.
If we look at different wavelengths, would that be any larger?
Not larger. We're pretty much picking up the outer extents here. But if you look online, there was a NASA probe called GALEX, G-A-L-E-X. It was basically designed to look at other galaxies. But GALEX, which works in the ultraviolet, took an ultraviolet image of the Cygnus loop. And if you can find that online, it is a really awesome image. But I try not to show any fancy images. We look at stuff here fresh from the telescope. So yeah. Again, this image here was just taken. You know, this is not archived. We just took this with the telescope. Yeah. So this is expanding, and the debris here is expanding at about 373,000 miles per hour, or if you're a metric user, about 600,000 kilometers per hour. And it heats the surrounding gas to millions of degrees because of the fast moving shock wave. And we can see multiple parts to it here. So let me see if I can label or show you the individual parts again. So as mentioned, this part here, I hope you can see my pointer, the really bright part, that is NGC 6992. This part is NGC 6995. And there's a really faint part down here you can just barely see. That is IC 1340. And then again, we have 52 Cygni. And then we have NGC 6960 here, the Witch's Broom. So we have the Witch's Broom and what I call the Veil Nebula, but you can call it the Eastern Veil Nebula. And this is another famous part here called Pickering's Triangle. But you really should call it the Fleming Triangle. Because in 1904, what most people call Pickering's Triangle here was discovered photographically by Wilhelmina Fleming at Harvard Observatory. But it was named for Edward Charles Pickering because he was the observatory's director. So it's only named after him because he was the director of the observatory that took the image that discovered this feature, but it was Wilhelmina Fleming that actually discovered it on a photographic plate. So Pickering's Triangle, Fleming Triangle, either way. And then we have up here, NGC 6974, and somewhere up here, I think somewhere around here, probably the bright part, is NGC 6990 or 79. So there's quite a bit in here. So we did do some spectroscopic analysis. I say we collectively, not with our telescope, but with other instruments, where the analysis of its emission indicates that it contains oxygen, hydrogen, and sulfur. So again, we breathe oxygen, and they came from, like the oxygen in our water came from supernova remnants, just like this. So that is our first target for the night. And don't forget, this image right now is being uploaded to our cloud account. And after the session is over, I will download all the pictures, do a little bit of light processing, and then they will be available for download. And I'll give you the link here at the very end if you don't have it already. Okay.
Hey, Richard, I have a question about the last image.
Sure.
Is it possible to estimate how many stars were in that image?
Let's see.
I mean, other than just a lot.
The plate solve here. Can you see the screen with the plate solving?
Oh, wow. Okay.
So according to the stars found, is 25,183 stars.
Interesting. Thanks.
So I'll give you 5 minutes to count them. No, I'm just kidding. Someone confirm that. Okay, there we go. Yep, that sounds about right. Okay, so while I'm on the screen, I'm going to enter in our next target here. And I'm going to hit get coordinates, but I'm not going to hit acquire image. Oh, wait, first, I'm going to put in the proper focal length for the Takahashi. That is the kind of the down, the negative aspect really of ACP is it can only work with one telescope at a time. So it can't switch focal lengths for us. Okay, now where was I? Oh, I was going to go back here. And that's pretty close. But again, I want this thing to be centered in a very specific way. So we get, again, 2 targets for the price of 1. So usually this part goes really quick because I just tell it to go somewhere. But again, I want it to enter it just right. I don't think I have to be so particular, so exact here, but we won't take any chances. All right, so that looks pretty good. And we're again going to use the hydrogen alpha filter and take another 10-minute exposure. So it's going to do its thing in the background here. And we'll switch back to the old PowerPoint screen here. Okay, so here's where our next target is located. So we're going to move from here. You can actually see parts of the Cygnus loop here. I don't know if you can quite make it out, but there's parts of it here and here. So we're going to move from over here to over here. And so we're going to look 3 degrees east of Deneb, which you can see here, and about 1 degree west of the 4th magnitude Xi Cygni, which I can't tell you when that is, but we'll see it here close up. And we're going to, again, stay in Cygnus, and here's where we're looking at here. So you can't quite see the Veil Nebula anymore on here, but this is our next target here, which is going to be NGC 7000. and IC 5070. And of course, again, we're just 3 degrees off Deneb there, or 1 degree west of Xi Cygni. That's a Zeta, I think. My Greek letters are rusty, but Xi is around. Oh no, this is Xi. Yeah, so like 1 degree from like here to here, because this thing's big. So of course, as you can see, we're looking at primarily NGC 7000, the North America Nebula. And a lot of people mistakenly call this the North American Nebula, but nope, it is the North America Nebula. And so you can see that in the sketch here. You can see we have the West Coast over on the right here, because again, this is a telescopic view. And of course, often when you look through a refractor or a Schmidt-Cassegrain, you know, the image is mirrored. So the artist here drew it as they saw it through the telescope. So we have the West Coast and Mexico, and we have Florida, and you can see kind of the Midwest in Canada, and you can see IC 5070 here, but here you can't really make out any detail. So as you can see, this nebula is about 1,600 light years away, again in the constellation Cygnus. And we'll back up here and look at this slide, because again, we're just starting a 10-minute exposure here. This feature here is about 4 times the moon's apparent diameter. So again, this is a really significantly large object like the Cygnus loop. So that's why we're looking at it with the Takahashi. The plane wave would show a tiny portion of this target. And if you've this is observable. Both objects that we looked at tonight are observable, but they are difficult. You can see this in binoculars and wide field telescopes, especially if you have a UHC or a narrowband filter. Those really help. And this was discovered by William Herschel on October 24th, 1786, or maybe by John Herschel before 1833. So there's some question about that. And it was first photographed by Max Wolf in 1890, who gave it its name because it has an uncanny resemblance to the continent of North America. And it's not labeled on this chart here, but there is a 10th magnitude open cluster called NGC 6997 that roughly marks the location of Ohio, or kind of the Great Lakes. So the cluster is right around here, and we can try to look for that when the image pops up. All right, so we'll go back to our blank slide there, and let's switch back to ACP here and see how we're doing. So we got plenty of time here. We're just starting our 10-minute exposure, because that really helps to bring this object out in all its glory. And let me show you some behind the scenes pictures here. These are pictures or images that most people don't see. So here is the observatory computer. So this is the screen of the computer in the observatory that's directly controlling the telescope. So this here is ACP running. So again, I connect to ACP from my computer with the ordinary web browser. So you can see I'm logged in here, Richard Bell, that's me. So you can see I am the one logged into the telescope. And again, ACP controls, say, this program here called Maxim DL. Maxim controls the main camera that's taking the picture right now, and it also controls the auto guider here. So it controls the auto guider, and you can see the auto guider selected this star here. I have no idea which one that is, of course. I don't think anybody does, which was automatically selected by the computer, or by Maxim, I should really say. And it's guiding, and you can see it'll shift around there a little bit. The wind has died down, so you can see our Clarity 2 station here. I pointed out the weather station in the observatory picture here, and you can see it's still about 67 degrees, so about 20 degrees warmer than it is here in Michigan. The wind has thankfully died down, because when they first started up, it really was kicking up there. And look at that, 22% humidity. That just makes me sad, because it gets so humid here in Michigan. And here, This program down here at the bottom left is called M1 Oasis. This is what controls the roof of the observatory. We have, if I can bring it up here, there we go. There's the Sky X, which is the Sky version 10. So the Sky X. This, of course, is what controls the mount specifically. And of course, the telescope rides on the mount. So we have a software BISC mount. So that's why we use the Sky, because they created, software BISC created both the Sky and the mount that we use. So that's why we have the Sky. You have to have the Sky to control the mount. And we'll make that go away. And you can see the focus program here called, appropriately enough, Focus Max. So this is what's, all this stuff here is what's actually controlling the telescope, and ACP controls the programs that control the telescope. So we still got a while to go here. So I'm going to stop sharing the screen. And we have some time for people to, perhaps introduce themselves. You can do it verbally or by chat, or we have plenty of time for other questions about the KAS, the observatory, the telescope.
I've been following this with the planisphere that you mail out to your members.
Oh, great.
And it's quite interesting, because I'm looking at the full sky on the sphere as opposed to the close-up focus that we have with the telescope. And it gives you a little bit better concept of what we're doing.
Hey, Richard, this is Dana. I'm not hearing anything.
Oh, I'm back. I think I muted myself.
Yeah, thanks.
I must have hit the button by accident.
It's really nice to have these programs. We appreciate you putting them on.
Yeah, it's great. It's actually, I always like to start the session by saying it's cold and cloudy, but tonight here, it's just cold. Because it is crystal clear here in Kalamazoo, Michigan, which is really unusual. Usually we don't enjoy many clear skies this time of year. So it looks like the image here is reloaded. So the car that drove by was gone. I don't know if you saw the glare from the car. And
what does ACP mean?
ACP stands for the Astronomer's Control Panel.
Thank you.
And again, that is the program that controls the programs that control the telescope. Oh, looks like the, I think it's, I'll hit reload here. Our PE sheet cam, as I call it, freezes quite often because again, we only have DSL out there. So with images being uploaded and stuff like that, sometimes the camera stops. But if you reload it, it goes well. And you can see, you can tell when the camera stops because the light stops blinking. So you can see the blinking light here on the Takahashi. So again, it's the little scope that's taking the picture right now. You can see, I mentioned that Mike Patton had a solar telescope. That's his Coronado over here on a pier. And unfortunately, we can't turn the webcam and show you the other telescopes. You can see this little screen here. This is our flat field screen for the main telescope. The Takahashi has its own little flip-flap flat field screen here. So we can take proper flats to help remove vignetting, you know, darkening in the corners. That's not such a big deal for the Takahashi, but it is for the plane wave. And we can get rid of dust spots and stuff like that with flat fields. Our pier here is about 2 feet high. This little box here is our industrial strength USB hub. And you can see we got a lot of cables being run through the mount here, but it looks pretty neat and organized.
How many people did it take to assemble this particular?
We took in our gallery section, you can find a installation of the remote telescope gallery. It's in these special events. And there's a picture of like 6 of us putting the telescope on the mount. But it was a group effort. You know, many of us helped. Let's see, all the people that were involved with the initial installation was, of course, myself, Jim Kurtz, Rich Mather. I'm probably going to forget people. Of course, Mike Patton helped. On the second trip, I know Mike Cook was there. Mike Cook should be joining us here tonight. He did register. Mike, are you here?
It looks awfully heavy.
It is. I'll give you the breakdown of the big scope here later. So let's, before I do that, let me, it is so hard to switch tabs on the web browser because the Zoom gets in the way. Oh, our image is done. So, well, that went fast. All right, so we should be back to the web browser here, and whoa, that looks much better. Nicely centered. Of course, it looked good before, but now it's nice and centered too. All right, now we heard the dong there a lot faster, at least I did. It's really loud in the headphones here. And it's done. So let's check it out. Now, if you could, go ahead and unmute yourself because I love to hear the oohs and ahs. Are you ready? Here we go.
Oh, there's the oohs and the ahs.
Wow.
Yeah.
Oh, yes.
All right, I really appreciate that. I love both the oohs and the ahs. Okay, so let me tell you a little bit about the image here while you gawk at it. So the North America Nebula, at least, has a diameter anywhere between 50 to 100 light years, depending on the exact distance. And of course, what gives the North America Nebula its shape is interstellar dust. So we have what's called dark nebula here, basically just dark dust and basically star soot that creates the Gulf of Mexico here. And basically the North American Nebula is like an open window in a large dark nebula here. And so the dense portion resembling Mexico and Central America right along here is known as the Cygnus Wall. And I'll show you some images of this region up close later with the bigger telescope that one of our members took. And I think he's here, so he can tell us about him if he's here. And it's probably Deneb, you know, that bright star Deneb, that's the source that lights the nebula. Because for emission nebulae like this, you have to have a star or stars to provide the energy to illuminate the nebula. And so Deneb is a pretty hot star. It gives off a lot of ultraviolet light. It excites the hydrogen gas here and causes it to glow. So that's why we call it a emission nebula. But the star and the nebula are about 70 light years apart, but Deneb is a pretty powerful star. It's much larger, hotter than the sun. So that's certainly feasible. But there is another candidate called the 6 magnitude 06 type star called HD 199579. I'm not exactly sure where that is, but that could be another candidate that could light the nebula. But it doesn't necessarily have to be one star either. And the reason why I wanted to enter in exact coordinates is so we can see the little neighbor here, IC 5070, which is called the Pelican Nebula. So you can see, the dark nebula makes a little eye and a mouth here, and you can even kind of see the head of the Pelican Nebula. So this is just southwest of the North American Nebula. But even though they have different designations and different names, they are all part of the same interstellar, cloud, the same emission nebula in this case. All right, any questions about the North American Nebula?
Said there was like a globular cluster or something near Ohio.
Oh yes, there's an open cluster. That's right, and you can kind of see it here. Of course, it's very small, but that cluster NGC 6997 is right here, and that is an open cluster. I never noticed there's like two little eyes here with a nose. This is.
I have a question.
Yeah, sure.
I was wondering, in the period of time that people have been taking pictures of this, does the shape of the North American change remarkably in any way?
I haven't heard of any changes in this. As mentioned, the first photograph of this was in 1890. I'm guessing if we had high enough resolution images back then and today, we could probably notice some changes, but we don't. I've never heard of any myself with this particular nebula. With objects like the Veil Nebula or the Cygnus loop that we just looked at, the answer there would be yes. We've noticed a bit of change there. And most definitely with objects like the Crab Nebula, which is a much more famous supernova remnant because it was made in the year 1054, at least from our perspective, given the time it takes light to get there. But the Crab Nebula has definitely changed, and as well as other supernova remnants. But this particular object, I'm not sure if we've noticed any significant change.
If we could, I imagine then we could find out how fast it's expanding.
Yeah. And it might not even be expanding. It's just a matter of bright stars are illuminating the structure. It'll probably change with time, but it's not like an expanding shell like a planetary nebula or a supernova remnant.
Yeah. Well, they're not stable things. They're always in movement.
No. Yeah, they will dissipate over time because eventually, these objects make lots of young hot stars that give off ultraviolet light and strong solar wind, and eventually it'll dissipate. Yeah, so they don't last forever. The sun could have been born in a very similar type nebula, maybe not this big. It could have been bigger, could have been smaller. We'll never exactly know. But yeah, this is where there's stars in the process of being born in here. So we saw an example of stellar death, and now we're looking at an example of stellar light. But both these objects, both the Cygnus loop and the North American Nebula, are in the Milky Way galaxy. Now we're going to look at something that is not in the Milky Way at all. And I'll type in M31 here, and this time I can just hit get coordinates and go to it. And off we go.
Hey, Richard.
Yeah, Mike.
I never really asked or thought about it before, but how much depth is there to that gas? I know we're looking at it on a plane. How much, do they have any idea how deep it is from that perspective?
Yeah, that's a good question. I don't think we know it. We're not even certain to the exact distance to this object because, normally we measure distances by, the parallax method. It's definitely too far away to measure by parallax, look for shifting stars as the Earth orbits the sun. And I don't believe there are any, like Cepheid variable stars that we use to measure distances. Okay. Definitely no type 1A supernovae. So I'm not sure how deep it goes. It's probably, 10, 20 light years or so.
Okay.
Because I think it is bigger. It is bigger than the Orion Nebula. Because the Orion Nebula is nowhere near 50 light years in or 50 light years across or deep. So so it is even bigger than the Orion Nebula. Okay, so I mentioned the Cygnus wall here, and let's see, I could Henry, Are you there, Henry? I see your name. Hey, Henry. Since you're here, do you want to tell us about this image?
Sure. I took this last season or a few nights, and this was like my first big project with the remote telescope. I edited this, stacked it in Deep Sky Stacker, and I edited it in mostly PixInsight, but a little Photoshop. It's a narrowband image, which means it uses narrowband filters like sulfur, hydrogen, alpha, and oxygen.
Yep.
And it's fun. It's a fun target.
Yeah. So as you can see from the second half of the name here, we're looking at the Cygnus wall. As I mentioned, the Cygnus wall was that part of the nebula that resembles Mexico and Central America. And the only time I show pretty color pictures like this during online viewing sessions is if they were taken with our telescope. So again, Henry here, Henry's just a 16-year-old kid, you know, even before he could, I think, legally drive, he was driving our telescope, right, Henry?
Yeah, this was like 5 months before I got my license.
Yeah, there you go. And I'll show you the second image here. So you can tell us about this one here, Henry. Of course, it's the same image, just a bit different.
Yes, the same picture with a little less, I think it has a few less data. I don't remember, but this is a different like color palette. This is hydrogen, oxygen, oxygen.
Yeah.
Instead of hydrogen, sulfur, or sulfur, hydrogen, oxygen. So it's different color mapping. I think this was the first picture I added in PixInsight, so it's not as nice as the last one.
Yeah. Yeah, they're both great images.
Very nice.
Yeah.
Very nice.
Thank you.
All right, so we're working on our last target with the Takahashi, and you should all know our last target with the Tak. We're going to look right here in the constellation of Andromeda, and here we have the Great Square with the star Alpheratz. So again, you can see the upside down head of Pegasus the horse with kind of the straight leg here, but you can see it can bend off here, and this one bends off. So there are two legs to the horse. The others are lost, because these stars here are Andromeda. So if you start from Alpheratz, go to these two stars, then these two stars, and just kind of point up a bit, about 1 degree west of this star here called New Andromedae, and you can find, of course, the Andromeda Galaxy. So this was first noted as a small cloud in the Book of Fixed Stars by the Persian astronomer Abd al-Rahman el-Sufi in the year 964 CE. And the German astronomer Simon Marius was the first to describe M31, the Andromeda Galaxy, which it wasn't called that yet, after observing it through a telescope in the year 1612. And Charles Messier, he did not discover it, but he included it as the 31st entry in his Messier catalog in 1764, because to him, through a small telescope, it kind of resembled a comet. And the Andromeda Galaxy, as we call it today, is the nearest big galaxy to the Milky Way. So as you can see from our little data slide here, the Andromeda Galaxy is only 2.5 million light years away. And yes, that's tremendously far away. But for a galaxy, that's incredibly close. It's not the nearest galaxy. There are lots of galaxies that are smaller that are closer to us, but the Andromeda Galaxy is the nearest big galaxy to the Milky Way. And it's often considered the most distant object you can see with the unaided eye. It's not 100% true. There are more distant objects you can see if you have good vision in really dark skies. And of course, the Andromeda Galaxy, along with the Milky Way, is a member of the local group of galaxies. At present, the local group contains about 55 known galaxies. And of the bright galaxies, the really bright ones, the 55, about 14 are dwarf ellipticals, 3 are spiral, and 4 are irregular. So you can see a map of the local group here. We put the Milky Way at the center just because we're the ones making the map. So outside of the sphere here, which is just a 500 kiloparsec sphere, you can see the Andromeda Galaxy. And this will be a target for the next telescope, the big scope M33 later. So we'll see two spiral galaxies in the local group. And of course, we have the large and small Magellanic Clouds here. These are both satellite galaxies to the Milky Way. Most of these galaxies within the sphere, I think most of them should be satellite galaxies of the Milky Way. I'm not sure if the two Leo galaxies are, but pretty much all the galaxies around here. In fact, this galaxy here, the Sagittarius dwarf galaxy, is so close, it's probably being absorbed by our galaxy right now. And you may have heard that in about 4 billion years, the Milky Way and the Andromeda Galaxy are expected to undergo a merger. So here's just a little video of that merger that could play out in the distant future. Of course, we won't get to enjoy it. Not even the Earth will get to enjoy it. It'll probably be absorbed by the expanding sun right around the time of the merger. But it might just make it, but it won't be livable. And you can see M33 over here. Some sources say M33 will get absorbed by Andromeda first, but here you'll see that it survives. I'm sorry to give you a spoiler, but there you go. So you can see the two nuclei merge along with their supermassive black holes, and that'll create gravitational waves. And the end result is a supergiant elliptical galaxy with perhaps M33 as a satellite galaxy. All right, let's see how we're doing. Oh no, I forgot to change the exposure from, I was going to do a 5-minute exposure, not a 10-minute exposure. Well, we're going to have one hell of an image of the Andromeda Galaxy here, because I can't stop it and have it load, because then it'll just stop and lose all the pixels. It'll lose all the data. So we'll just go ahead and let that finish up there. I forgot to change the exposure time. Maybe we'll do like a really short one too. We'll see how we're doing with time here. All right, so let's check on the all sky camera. We can see this red light down at the bottom left here. Mike Patton has like this lighthouse in his yard. You know, it's like some yard ornament, and it has a red light inside. So this is his lighthouse. Of course, there's no bodies of water out there, but you know, he has a lighthouse in his yard. You can see the summer triangle a lot more clearly. So we've moved from over here to over here. You can, oh, the Andromeda Galaxy has moved away from the black smudge, and it's this little smudge right there. So that's where the telescope is looking right now. All right, so we'll let that finish up. We'll come back to the Zoom screen here. And I have not checked the chat. I see some oohs in the chat. Yep, I had the sound off. Sorry. Sometimes I hit the button on my little headphone here by accident. So if you don't want to ask, I should have mentioned this earlier, if you don't want to ask questions verbally, you're welcome to put them in the chat as well. But I'd love to hear from you. One of the great things about this is we get to meet other people. So you can't meet anybody because I can't see anybody or hear anybody.
Just a quick question for Kathy Coons. What is that a picture of? Is that a cave or?
It is a cave. It is, if you could expand it, you'd see where I have my hand right there, animated hand. It's either a walkway or it's people. That's how humongous this cave is. I don't know where it is. I'm thinking it's Australia, but I'm not sure.
I had a question about like the images that Henry took.
Yeah.
How big? I think the second one, the exposure time was like 8 hours. How big of a file would that be?
Well, each individual file is 32 megabytes, but Henry will have to, I don't know if Henry has it handy to tell you the final exposure of the fully processed version.
I'll tell you the stack and I'll tell you the final.
Okay.
Wait, what'd you say? Sorry.
He's going to check on the stack, you know, because you.
Oh, awesome.
we stack all the images together, and that'll give you the total file size.
Right. Thanks.
Yeah, because each individual subframe is 32 megs. It doesn't matter if it's a bias or a dark or a flat or a light image. It's 32 megabytes, no matter what. Which is good enough for us. I know some images from the higher res cameras are, yeah, we can show, of course, the telescope isn't going to be slewing there, Craig, but we can show the telescope if I can find it. There it is. So there's the current position of the telescope. So you can see we're looking in the opposite direction now. Again, this is the north wall here. You can see, again, our flat field screen. This is our club logo. You can kind of make out the door here. We have a pad on the door here because one of our members kept hitting his head on the door. So we put this pad there. Even though he's not there very often, we left the pad there for safety. You can see this tree start, like the shrub growing beyond the wall there. As soon as Mike Patton gets there, he says he's going to knock that down a bit, give it a trim. But it doesn't really interfere with the telescope. We never look quite that low. And you can see the infrared light from the webcam is reflecting off the reflector here that we use for the sensor when the scope is parked. So we know the scope is safely parked when we roll the roof back on, because if we roll the roof back on, it would kind of shear the truss tubes off. That would be bad.
Okay, so the final image is 252 megabytes, but interestingly, all of the stacks are 32.
Yeah. Wow, that's a lot smaller than I thought.
Yep.
I have an Orion Nebula mosaic that I'm working on, and that's a PNG. The test image is only 530, and that's 12 frames taken at the Takahashi.
Okay, thanks. Interesting.
Mm-hmm.
All right, so let's see what we got here. Oh no, I forgot to switch filters too. So this is the Andromeda Galaxy in hydrogen alpha. Oh boy, that went really bad. So let me try. Let's just do 3 minutes with the luminance filter, and we'll do that one again. We'll just do a shorter one because even 3 minutes looks really good. So I really apologize for that, but I'm working on a large image of the Andromeda Galaxy now, so I can use this H alpha image for that. So it's not a total waste of time, at least not for me. So, oh, you can tell this is our first session of the season because I'm really rusty with trying to switch things over really fast. Usually when we're taking pictures, I have plenty of time to think about what I'm doing. So we'll do one more quick one here. And you can see it's doing a 20-second picture. This is for the plate solving. So it's right centered, because as soon as the image is done, when it's not imaging, the mount turns off. It doesn't track for safety reasons, in case you forget about it and let it track all night, you know, and it collides with a pier or something. So when it's not taking a picture, the mount stops. So that's why it has to replate solve, because it has moved a little bit. And we can kind of look in the we can look in the background here and see what's going on. This is probably the last guide star. So there's a selection of possible guide stars. This one is for sure too bright. It'll probably use this one if I guess right, because it usually likes to faint ones. But there's no way to know, because you can't tell from the little box there which particular star it chooses. And now you can see the guider is settling, and now it's doing a 3-minute exposure. So you can see it's really easy to control the telescope. You just have to remember to change filters when you want to. So it certainly wasn't a technical error, it was a user error. But the really good news about this session is this is the first premiere session where we could actually use the Takahashi. For the very first season, We had some bugs with the new scripts. So we couldn't use the Takahashi because of the bug. We had to use just the big scope, which maybe most people prefer anyway. And then last year, the filter wheel came loose a little bit and it wouldn't change. So we couldn't change filters. So we had to wait for Mike to get back out there to tighten down the filter wheel. So this year is the year everything's working great, and we can use the Takahashi. But don't worry, we will do 3 images with the big scope too. But we got to get one of the Andromeda Galaxy here, at least one I think you'll enjoy. I mean, hydrogen alpha is great. We could go back and look at that, and I can kind of tell you what you're seeing. Yeah. So of course, this is the very center of the galaxy, which contains like hundreds of millions of stars. Mm-hmm. And you can make out the disk here, but where it's brighter, that's where you have emission nebulae, like say the North America Nebula or the Orion Nebula. So, you know, the stars themselves in the galaxy give off very little hydrogen alpha light. So that's why it doesn't look very impressive. But what the hydrogen alpha does is it really picks up the light emitted by the bright red, you know, emission nebulae. So that's what we see. And you can make out one of the satellite galaxies. There's a satellite galaxy here, M110, and this is M32 up here. So there is stuff to see. You can even make out a little bit of a dust lane here, just because the core is so bright. But pretty much you don't see a whole lot here.
How can you tell that's a galaxy, that little itty bitty thing?
Practice.
Okay.
I've looked at it many, many times, both visually and photographically. So that is definitely the Andromeda Galaxy. All the little galaxies are in the right place. All right, 10 seconds to go. And it is so weird. It goes 6 seconds over in the count. I don't know why it just doesn't stop. There we go. That looks much better. Okay, so the thumbnail has loaded. Now we'll wait for the actual image to load. Whoa. Oh, that is so loud. I don't know if you guys can hear that, but I can. It's very loud. There we go. Isn't that beautiful?
Oh,
nice.
Wow. And that is only 3 minutes.
It's amazing.
So a little bit about the Andromeda Galaxy. As mentioned, it is the largest and the most massive galaxy in the local group. So wow. It is larger than the Milky Way. You know, our galaxy is about 100,000 light years across. The bright portion of the Andromeda Galaxy, like roughly from out here to here, is around 130,000 light years. But as you can see, thanks to the really dark skies, it extends further than that, like roughly out to here or here, probably further. And that brings it out to 220,000 light years across. Our galaxy contains between 200 to 400 billion stars. And this big flat disk here is about 1 trillion stars. It weighs 1.5 trillion times the mass of the sun, 1.5 trillion solar masses. And our galaxy weighs about 850 billion solar masses. Our galaxy contains a 4.31 million supermassive black hole. Deep in the nucleus here is a 100 million solar mass black hole.
Don't bite me.
As mentioned, oh, someone's getting bitten. Right here is the galaxy M32, which is a dwarf elliptical galaxy. That is 24 arc minutes south of M31. I should say M31's nucleus. It's about this little sphere here, this little smudge is about 6,000 light years across and contains 400 million stars, which is dense. It's one of the densest known galaxies. And it may itself contain a 2.5 million solar mass black hole. And then out here we have M110, the last object in the Messier catalog. And it's also known as NGC 205. This contains 10 billion stars here, which is in a elliptical sphere about 16,000 light years across. But even though it's a really big galaxy, there is no evidence for a supermassive black hole here. So there you go. There's the Andromeda Galaxy. And you can make out brilliant dust lanes in the galaxy. This little bright smudge is a dense star cloud in one of the spiral arms. So there you go, the Andromeda Galaxy. Any questions about Andromeda before we move on? I should mention, when you download the files from tonight later, you will be able to zoom in. This is a shrunken version for display here, but it's, it takes time to go get the images and download them and do a quick processing. So we really can't do that here, but that'll be the really cool part, is you can get the full resolution versions later and zoom in and see even more detail. Okay, so before I forget, because as you guys saw, I will forget, we're going to switch telescopes now. So I'm going to enter in the data for the other telescope because it's time to switch. And we have a little script just for that down here somewhere. So we'll switch telescopes. And while we're doing that, let me tell you about the big scope. All right, so here it is during the day in wonderful color. So you saw the logo. Ooh. And of course, here is the Takahashi again. And here's our big boy, our plane wave CDK 20 telescope. So this is a CDK, which means a corrected dull Kirkham, which a dull Kirkham means it has a ellipsoidal primary mirror and a secondary mirror with a lens group in the back. That's why it's corrected. So it's a corrected dull Kirkham. There's like a lens group back here that makes it corrected. So it's coma-free with no stigmatism and a flat field across a 52 millimeter plane, but it's not totally flat for us because we had to move the secondary mirror back a bit to be able to reach focus with the stuff we have on the back here that I'll show you here shortly. So we do have some vignetting in the corners, but with flat fields, that's easily corrected. So the 20 in CDK 20 means it has a 20-inch primary mirror made of quartz. You can see the long focal length here, 3,454 millimeters, but that is shorter in focal length than the 16-inch Schmidt-Cassegrain that we have in our observatory here in town. And it's a nice focal ratio speed, f6.8, so not too slow, not too fast. And you can see it is quite heavy. The 20-inch alone weighs 140 pounds. And it does have pretty much an all carbon fiber construction because of thermal expansion issues. And here's the back business end. So again, we have the same camera on both scopes, the same filter wheel. But here you can see we have what's called an on-axis guider. I won't go into too much detail about what an on-axis guider is. And we have our current auto guider here, but we're getting a new one. The newer auto guider will have 5 times the field of view of this auto guider. So we've had issues looking for guide stars and fainter, more obscure parts of the sky. And the larger auto guider will hopefully solve that. And here's the mount before we put the scopes on. Back in 2015, it's a software bisque Paramount ME2 with a 240-pound instrument capacity, 480 pounds total. And it is an excellent mount. I won't bother to give you the juicy details there. So we should be able to go to our next target now. Let me get back to the browser here. Yep. And we will go to our first target. So I don't have to make a huge change here. We'll do M30, so it's just one down. And I got the right filter this time. 180 is probably a little on the long side. Let me try 2 minutes. That might even be a little bit too long for the 20-inch, but we'll give it a shot. So let me show you where we're going now. So now we're going to go down to the south in the constellation Capricornus, the Sea Goat, which again looks like a Cheshire cat smile. So I mentioned Sagittarius, the teapot. So you can see a bit of the Milky Way here, but we're getting off the plane of our galaxy, kind of south of the galactic plane, towards some of the constellations that we have a hard time seeing here. We can see Capricornus, but we have a hard time, at least from my latitude, seeing Microscopium, Pisces, Austrinus, and Sculptor. But we can see them from Arizona because we pick up 10 extra degrees there. And here's a zoom in of where we're going. So as I typed in there, we're going to M30, which is a globular cluster in the constellation Capricornus. It is 23 arc minutes west-northwest of the 5th magnitude binary star, 41 Capricorni, which is right next to it. We'll probably even see it in the field of view. And it's about 3 1/3 degrees east-southeast of the 3rd1/4 magnitude star, Zeta Capricorni, right here. So it's kind of an easy star hop from, say, here to over here, but it is kind of in a faint part of the sky. It was discovered by Charles Messier on August 3rd, 1764, and he described it as a nebula, you know, because of his small telescope. And he noted it can be seen with difficulty in a simple refractor of 3.5 feet. That was the focal length, because back in his day, they referred to telescopes by their focal length and not their aperture. And then he went on to say that it is round and does not contain any star. Obviously, he was very wrong. But through his telescope, it looked like a little fuzzy comet, so that's why it's part of his list. Now, William Herschel observed this object in 1783 and wrote in his personal notes, a brilliant cluster, the stars of which are gradually more compressed in the middle. The figure is irregularly round. The stars about the center are so much compressed as to appear to run together, which is a pretty good description of a globular cluster. And if you've made notes of M30 visually, you may have noticed that it has a lopsided appearance, with the northern portion displaying well-defined kind of fingers of stars, while the south part looks kind of needed but incomplete. With the image that we'll get from the 20-inch, it'll probably look totally symmetrical and even, but visually it does look quite lopsided, as you can get a hint of in the sketch here. So I can hear in my ear that it's trying to find a guide star. Let's see how it did here. It still worked. Oh, uh-oh. We might not get a guide star this time. So that's why we're going to get a bigger guider. It'll try to guide here for a while. It'll look for a guide star for a while, but eventually it'll just give up and take a picture. And at 2 minutes, unguided, it shouldn't be too bad. So it's going to take a little longer here because of the lack of the guide star. It's going to try to keep looking for one. Oh, nope, it's taking the picture now. I was on the wrong tab. All right, am I back on the ACP screen here? Can you guys see that?
Yep.
Okay.
Yes.
All right. So it gave up looking for a guide star. I don't believe I've ever taken a picture of this with the 20-inch before. So I wasn't sure if we'd get a guide star or not. I was going to rehearse some objects last night, but it was cloudy out there last night. And thank goodness it's not cloudy tonight. Otherwise, we would have postponed till tomorrow. All righty. We'll let it run in the background there. So again, we got plenty of time for people to say hi, tell us where they're from. Questions? comments?
I have a question.
Sure, please, Kathy, go ahead.
You probably have already mentioned this and I don't remember, but whose property is the scope on?
It belongs to Mike Patton, who is one of our members.
So he lives in Michigan and
Yeah, he
Arizona?
spends kind of mostly the summers in Michigan, because if he were here, he was going to join us tonight, but looks like he couldn't quite make it. He does not like rattlesnakes or scorpions. So during the summer, you know, it's nice and hot out there and they are really active. So he comes here in the summer and he spends roughly November to March or April out there. So for the next 3 sessions, he will be there. You'll probably see him walk in front of the camera. And let's see. So there's the scope now. You can see we are looking low in the south. And I just heard the image is done. So let's hop back to the picture there and see how we did. Looks like we got something.
That scope moves very quickly.
It does. So there it goes. There's M30. So it obviously is a globular cluster. The true physical size of this thing is about 93 light years, and it is old. It has an estimated age of 12.93 billion years old, which is typical of this object. That's on the higher end for globular clusters. And it has a total mass of about 160,000 suns. I'm not sure how many stars it contains in all. I couldn't find any source that mentioned that, but it's probably in the realm of 30 to 50,000, I would guess. And as is typical of globular clusters, it has a very low metallicity, very low metal content, which means the stars in this cluster are made up of pretty much nothing but hydrogen and helium. And if you talk to an astrophysicist, they might mention that, you know, stars in this cluster are metal poor. And what they mean by that is they don't have any other elements besides hydrogen and helium, because to the astrophysicist, anything beyond hydrogen and helium is a metal, even like oxygen, because the metals were made in stars, you know, made in objects like the Cygnus loop that we looked at earlier. So this one is 1/100th the metal content of the sun. So it is very metal poor. It orbits the galactic center, you know, the center of our galaxy, at an inclination of 50 degrees below the galactic plane, which I pointed out in the chart earlier. And it takes about 160 million years to complete one orbit around the galaxy, which is pretty quick compared to the sun. It takes the sun about 240 million years, while this cluster takes about 160 million years. So its inclination makes its distance from the galactic center vary by about 10,000 to 25,000 light years. So it's a fairly eccentric orbit. And it follows a retrograde orbit, which means it orbits the opposite direction from most other globular clusters and material in the halo. And this fact that it orbits backwards tells us it's probably from a captured satellite galaxy. The Milky Way absorbed the satellite galaxy most likely, and it kept the globular cluster unharmed. And that may also explain why the metal content is so poor. One thing you'll notice is the core is pretty overexposed. I was kind of worried about that because the core stars are very densely packed. The core itself measures about 1.9 arc seconds. And this shows us it has suffered something called core collapse, where one star in the center kind of goes array. It disrupts the motions of the other stars, and that just makes them kind of come really close together. We think there are roughly 1 million stars per cubic parsec. So say between the sun and Sirius, about 9 light years away, there'd be millions of stars between that distance just within 8 light years. Another unusual thing about the core that you can't quite tell from the picture is it contains an unusual number of what we call blue stragglers. You know, because typically the stars in this cluster are, you know, yellow or red, but it has a lot of blue stars called blue stragglers that are either the merging of 2 stars or by the mass transfer in a close binary system that gives it a blue color. And if you do observe this cluster through a telescope, the very center does look blue because of those blue stragglers, and that's really unusual for a cluster of this class. So you can tell the stars are maybe a little bloated. They might be a little trailed because we couldn't find a guide star, but we're hoping to fix that soon. And also we're looking pretty low, and the seeing may not have stabilized too much yet.
So the center is dense, but it doesn't have a black hole?
As far as we know, it does not. And what I've read over the years, this does not contain a intermediate black hole, because these objects do not contain like stellar mass black holes, like from the collapsed core of a massive star. It's not a supermassive black hole, so it'd be an intermediate mass black hole, maybe 10,000 to several 100,000 solar masses. All right, any more questions about M30? This is our first time on this target.
Hey, Richard.
Yeah.
What is the object in the upper left corner there?
That's that's the star, what was it, 41 Capricorni.
Okay.
And again, you can see we got some vignetting here. That means the field isn't totally illuminated, but again, with flat fields, we can fix that.
Yep. All right.
But you have to take like a whole bunch of them to do it.
Did you say you wanted to see binaries?
There are binaries, but they're too close to really, they're too smashed together to really pick out. So they are in there. Okay, so let's do our next target. I think I'll try 5 minutes this time with the luminance filter. Now let me do something that I haven't done yet. Let's go to the Edge browser. Let me hit reload there real quick in case it paused on me. And let's see if we can catch the telescope move. It's not going to move very far. This target's not too far away. There it goes.
It moved.
It moved. That's it. I told you it was close. I guess I picked the wrong object to see the telescope move. So boy, that was really exciting. We'll try it again for the next one. Okay. So here's where we're going now. We're going to go probably a little bit lower, but I don't know, it looked higher to me. But we're going to look right below Cetus the Whale here. This is a pretty difficult fall constellation to find. Way below the Great Square here, and even Pisces the Fish. And we'll kind of go from Diphyta here, and you'll see it here, and that's our target. So this thing is about 3 degrees southeast of Beta Cedae there, Diphyta, which marks the whale's tail, according to some sources. And this target here is called NGC 247, or the Needle's Eye Galaxy. And you'll see why we call it that. And as you can see, it's 11.1 million light years away. So it'll be the most distant target we've looked at thus far. In fact, it's the most distant target we'll look at tonight, because our last target is even closer. It's roughly the distance of the Andromeda Galaxy. But even at 11.1 million light years, it is among the closest galaxies to the Milky Way. It's definitely in like a top 20 list. It was discovered by William Herschel on October 20th, 1784. And it is also known as Caldwell 62, because it's the 62nd entry in Sir Patrick Caldwell Moore's catalog, the Caldwell catalog. And this is often overlooked since it's near a much more spectacular galaxy called NGC 253, the Sculptor Galaxy. And you might be wondering, why aren't we doing the more spectacular galaxy? But guess what? We did that last year. So I try not to do too many repeats. Now, the Andromeda Galaxy, we do that one every year because everyone demands it. But I try to, we try to shuffle around a little bit to have some interest. But maybe we can do that as a bonus object later, because I don't plan on doing that one this year because we did it last year. But bonus objects don't count. And this galaxy is, again, pretty far south. It lies 6.5 degrees from the south galactic pole. So we do see it mainly unobscured because it's so far south of the Milky Way. Dust from our galaxy doesn't really block it out. And pretty soon you'll see why we call it the Needle's Eye Galaxy. So now we go back to the screen here. Oh, we didn't get another guide star. Oh, darn. So it's going to do a 5-minute exposure unguided. So we're going to have a bit of trailing here for sure, but not too bad. The Paramount does pretty well, but even 5 minutes is a little long for unguided. So again, you can see why we're getting another guider with a larger field of view, because that has been an issue in obscure parts of the sky like this. But this target is one of the reasons why we really like to do these online viewing sessions, because again, this is one of the targets you can't really look at with a telescope, at least from our latitudes in the US here. Maybe if you're really far south, and, you know, again in Texas or Arizona or New Mexico, but from Michigan, this is a target I've never observed visually. I don't think I've ever observed it visually at all. So we do some challenging objects too, as well as the bright showpiece objects. And we will definitely end with a showpiece object, at least with the telescope. All right, so we're still chugging along there in the exposure. We do have time for questions and comments and introductions. So it'd be great to hear from some of you. We got a shy group here tonight.
Hi, Richard. This is Dana. I'm happy to talk for a minute.
Okay.
Roy and I live in Central Ohio. For people that don't know us, we are associate members. We see our sky at the John Glenn Astronomy Park, which is down in the Hocking Hills area. If you ever come down this way, it's what, almost 4 Bartle, is that right?
It's a little less, like 375.
So it's not as dark as you might get, but it's nice. Hiking Hills is a great place to come for a weekend and go hiking. And at the Astronomy Park, people come to watch the astronomers, and they do laser shows with the stars. But the last 2 nights, and tonight also, have been just spectacular. First time in 3 months we've had clear skies.
And you guys aren't outside imaging?
I've been there 2 nights in a row, and that sort of wears you out.
Yeah, because of the cold dip.
Yeah, so we're hoping to go tomorrow night if it's clear. The weather forecast is iffy.
Yep.
Well, actually, another question related to your remote telescope.
Sure.
Here in Ohio, even when it's clear, we like our skies wet. So you always have a dew shield and a dew heater on.
Uh-huh.
And apparently you don't need either of those in Arizona ever?
Ever. I've never seen the humidity more than 50% out there, ever.
You get every advantage.
Yep.
So my brother lives a little outside of Benson, which is of course east of Tucson. And if we were to take a trip down there in the middle of winter, are there places we can stay?
Yeah, there are like bread and breakfasts at Arizona Sky Village.
Okay.
Well, okay.
I can't reference one offhand, but there are at least 1 or 2. And there's even like a nearby, there's a hotel in Portal, I think. If you can call it a hotel. It's not really in it's not really in the town, but it's right nearby. We were going to stay there, but another resident allowed our members to stay in his house while he was away, because he's like hardly ever there.
Mm-hmm.
All right, I think I heard the image wrap up there, so let's go back to the browser. And pretty soon here, the thumbnail will pop up. And then we'll give the actual image a second to load. Oop, there it goes, bong, bong, bong. Well, I don't see anything. Uh-oh. Did I goof up again? Hang on here. I am just batting 1,000 tonight. Hang on. I think I forgot to maybe hit the get coordinates. I did. So we took another image of M30. Oh man, I really sorry about that. So let me show you what I forgot to do. Share the screen, go back to the browser. So I typed it in, but I forgot to hit get coordinates. And you can see it's changed. Rats. So let's try it again. We did see the telescope move too. So it should have moved a little further than it actually did. So let's see if we can go back to the scope and see it actually move. So I am just doing lousy tonight. But it's the first session in 9 months. Oh, there she goes. Now she's really moving. It might even have to go to the other side of the meridian. All right, so now we get to see the telescope really move. I wish there was sound. Would anyone like a sound effect? That's the best I can do. It's actually more like you know, they're very good motors.
You're pretty good.
Yeah. So that's not too bad. It's not for me, it's not too jerky. Sometimes it can be a little jerky because again, that DSL is our arch enemy out there. It is painfully slow. There's the infrared light shining off the reflector again. There is another webcam in there. It's a FOSS cam, but that's going to be turned off until Mike is back out there. But this is our webcam here. When I actually image with the scope pointing in this direction, I tend to turn the webcam off because I want to make sure I don't get any interference from the infrared light. I've tried to see if I could detect any. You know, I've taken pictures like this with it on and off, and I don't notice anything. But just to be safe, I turn it off. One thing I was going to mention, because it is the desert, there's lots of wildlife out there. When I was getting ready, I saw a little mouse running back and forth on the I-beam here. Sometimes you'll see him right on top of the rail, or right on top of the I-beam. But tonight he was on the bottom of the I-beam, just kind of running back and forth. All right, let's go to the computer.
Don't you have to be careful so that they don't nest in there and think
we haven't. Oh, no guide star again. My goodness, look at that. Blank. We haven't had any issues like that yet. We haven't had any chewed cables that I remember.
Good.
So we've been lucky. He did. Mike did try one of those mouse repellent sensors, you know, that let out a high frequency noise, but apparently they don't work with the mice out there. They work like a charm in our observatory here in town. We haven't had a mouse issue since we put one of those mouse repellents in there. Okay, so no guide star again. You can really see why we're getting a new auto guider. I hope it helps. So we just started the 5-minute exposure there. So again, we got plenty of time. We will, you know, we do plan to go 2 hours from 9:30 to 11:30, but we did start a little late because I was waiting for it to get dark enough out there. That won't be a problem next month. Because right now from Kalamazoo, we are 3 hours behind Arizona, but in just about 3.5 hours, we'll be 2 hours behind Arizona. So I'm really hoping we stay on standard time forever. But I've heard talk in Congress, they're talking of doing something called the Sunshine Protection Act, where we just stay on daylight time, which I don't want. I want to stay on standard time. So it gets dark a little earlier.
Yeah,
So
it plays havoc with the farmers.
Yeah.
You know, because animals, they have that internal clock going, and they don't care what the clock on the wall says.
Nope, they don't. They have no sense of daylight time. They get the same hours of daylight. They just don't look at a clock. But yeah, it changes the farmer schedules, and that freaks out the animals. I don't even see anything in the chat. You guys are the quietest group we have had so far. My goodness.
Well, we like to listen to you talk.
Oh, I'm not that good. I'm no Neil deGrasse Tyson or Carl Sagan.
I had a question just about the observatory computer.
Yeah.
I think I saw VLC was running. How does that fit into the loop?
That's what gives us the PE cam.
Oh, interesting. Okay.
Yeah, that's how we do the streaming with the PE cam.
That's cool.
Yep. So this is a VLC giving us this picture right here.
Oh, wow. Okay.
Hey, can you guys see your reflection in the mirror? There I am. Hi. Let's see how we're doing.
If our members would be interested, there's a book called The Day We Found the Universe by Marcia Bartusiak. She's a science writer, and the focus is on what Hubble did and how he discovered the galaxy aspect of the nebula. And she actually, I spoke to her once. She actually held the papers that he marked when he made his discoveries. I think it's in Harvard or in their library. It's a pretty interesting book.
Cool. Boy, the horizon looks a little murky tonight, like there's maybe dust being kicked up. So
yeah, I was thinking about those dust storms they hit in Phoenix a couple years ago. It looked like the end of the world. And
yeah. Well, we'll go back to the screen here. Let's see how we're doing with ACP. Almost there, about 40 more seconds. So I do apologize for the mix-ups tonight, but I'm a little rusty. And for those of you in different clubs, I don't know how participation has been during the pandemic, but for us here in the club, it's been down quite a bit. So we're looking forward to really getting things back to normal. But the online sessions here, they'll always be online. I meant to do these online well before the pandemic started. So doing these online had nothing to do with that. So we plan to keep these online, in perpetuity.
So your club is much more active than the Columbus Astronomy Club in different ways. You're more, and I think it's because you're the driver, but your meetings are more focused. You have better planning that goes on. We've had, I'm the secretary, but I'm now acting president because both the president and vice president have resigned.
Oh, no.
Thank goodness elections are coming up next month. And I have a full slate of officers.
Oh, great. Here we go. All right. So finally, here we have NGC 247, the Needle's Eye Galaxy. So a few little facts about this one. You can see this one's about, of course, you can't see it. This one's about 70,000 light years in diameter. So it is smaller than our galaxy. And here's why it's called the Needle's Eye Galaxy. Go ahead and look at it. It's marred by an unusually large void on one side of the spiral disk. And the void contains some older, redder stars, but no younger, bluer stars. So maybe one explanation for this is an older galaxy that this spiral has absorbed. So there's the needle eye in the galaxy, which is this unusual region with these older, redder stars. And it is one of several galaxies that's gravitationally bound to the Sculptor galaxy NGC 253, which is more spectacular, but we looked at last year. And so this galaxy is a member of what we call the Sculptor galaxy group, kind of another poor galaxy cluster like the local group, with just maybe several dozen galaxies. And there is a string of 4 galaxies just below and left of this, known as Burbage's chain, which is 300 million light years away. But I don't think you can quite pick it up. There might be a couple of members possibly here. These do look like fainter galaxies here. So you can do some research on Burbage's chain right near NGC 247 here. All right, any questions about this galaxy before we move on to our final target for the night? All righty. All right, so our last target is M33. Whoop, don't do that. Of course, it won't go anywhere. And this time I'm going to make sure I hit get coordinates. There we go, it changed. And we're going to hit acquire image. So, should be back on the PowerPoint there. So here's where our last target is. The Andromeda Galaxy is up here. But now we're going to go to M33, which is just below or south of Andromeda, but technically in the constellation Triangulum. So that's why it's also known as the Triangulum Galaxy. And it is often referred to as the Pinwheel Galaxy, but that name is generally reserved for M101. And it was probably discovered by the Italian astronomer Giovanni Battista Dirna before 1654. And he noted it as a cloud-like feature near the triangle. Obviously, that's Triangulum. And it was independently discovered by Charles Messier on August 25th, 1764. And among the first, it's among the first spiral nebulae identified as such by a guy named Lord Ross or William Parsons back in 1850. And by the chart here, you can see it's 4 degrees west-southwest of the 3.4 magnitude Alpha Trianguli, right at the apex of the triangle there. And of course, as noted, M33 and M31 lie on opposite sides of the galaxy, or on opposite sides of and nearly at equal angular distances from Beta Andromeda here. So you can see they are pretty equally distanced from Beta Andromeda, at least in our sky. So here are a few basic facts about M33, the Triangulum Galaxy. And you can see it is a bit more distant than the Andromeda Galaxy. So this will be our second most distant target for tonight at 2.73 million light years. And it does have a fairly large angular diameter, but because it is smaller than both Andromeda and the Milky Way and kind of closer to face on, it's a low surface brightness. So it's not a great object visually, but as you'll see, the remote telescope will pick it up very nicely. So let's see how we're doing here. We got a guide star this time, yay. So, we're kind of closer to the Milky Way this time, so it makes more sense. There are more stars near the galaxy than away from the galaxy. And let's see where the telescope is. So we're looking really high this time too. No more of that down low in the south stuff, but it is fun to do that, to see stuff we can't see from here. And we'll take maybe another peek at the home computer. And yep, there's our guide star. And the wind is 6.5 miles per hour. I don't think it's ever exceeded 10. Normally, if the wind goes over 10 miles per hour, the telescope will park itself, but I did sort of change the rule for that tonight, so it didn't interrupt our session, because we would have to totally shut down and start over again, assuming the wind dies down, that is. So the wind is a little heavier than advertised, but oh well, it's hard to predict the weather. Let's peek at the, hopefully you'll see the all sky camera there now. That's what we're looking at now. So tell me if you can't see the all sky camera. The Great Square is pretty much due south now. And we're looking again, right about there. You can see the triangle here. Here's Triangulum, this little tiny constellation right there. And again, we're right about there.
Richard, could you point to the needle that we just looked at?
Oh boy, that's a hard one. Let's see. There's Aquarius starts here. This is known as the water jar. And then Cetus is over here. Oh, here it is. Okay, so here's Cetus. This is Dipheta. I think I'm saying that right, or Beta Aquarius. And 247 is right there. And you can see the tail of Cetus go off this way here. So yeah, we were looking here for M30. M30 is right here. And then we zoomed over here. So you can see why the telescope turned all the way around to go from over here in the southwest over to the southeast. And now we're looking way up there. And once the session concludes here, I'm going to be looking at a galaxy right behind the smudge here that I've been working on, called NGC 891, which we did look at last year.
What is that smudge?
Dirt on the dome of the all sky camera. No one's been out there since, mid-April or so no one's been there to clean it. Mike's been here in Michigan all summer. But by the time we have our next session, he'll be back out there. And when you look at Mike, Mike has white hair. So in infrared, he looks like a ghost. You can make out his face, but he looks pretty bright. So you'll see him walk back and forth occasionally. I keep telling him not to slam the door when we're imaging, but he has a habit of doing that. All right. We're almost done here with the last picture. Oh boy. All right, don't forget to unmute yourself for the oohs and ahs.
Ready.
Makes me happy.
This is a worthy ooh and ah-er.
It sure is. Here we go.
Oh, yeah.
Oh.
Gorgeous.
That's beautiful.
Great.
I know. Look at that.
All right, so this galaxy is, again, not quite face on. It's inclined 54 degrees, so not perfectly face on, but it does provide us with a pretty good face on view. And of the three major spiral galaxies, Andromeda, the Milky Way, and this one, this is kind of the dwarf of the bunch. It's only 60,000 light years in diameter and contains about 40 billion stars, like a tenth that of the Milky Way. So third largest member of the local group, and it's about 60% the size of the Milky Way. It is currently moving toward the Andromeda Galaxy, which again, there's a lot of suspicion. It is a satellite galaxy of the Milky Way, but it's not confirmed for sure. And M31 and M33, which we're looking at here, are less than 300 kiloparsecs apart from one another. And some say they will eventually merge about 2.5 billion years from now, but according to that simulation we saw earlier, M33 survived. And as I think I also, no, that was for another galaxy. Even though this galaxy is pretty big, it is not known to contain a supermassive black hole. So that is really unusual for a galaxy this size. And it does contain NGC 604, which I think is right here, the smudge right here. It really comes out in H alpha, but this is not an H alpha image. And this is one of the largest known emission nebulae. It's about 1,500 light years across, but it looks so small because it's over, 2.7 million light years away. And you can see it's a really wonderful spiral. Okay, so let's wrap up here. I just do want to give you a few plugs here. If you do live in one of these counties in red in Southwest Michigan, you can join the Kalamazoo Astronomical Society if you haven't already, and you can use the remote telescope. Besides the fact that I forget to hit, the button to look up the coordinates and switch filters, it's really easy to use. When I'm by myself working with the telescope, I rarely ever do stuff like that. So again, I'm really sorry about that. But again, we encourage member use of the telescope. Roughly 40 members have paid to use the telescope because there is an extra fee to use it. And not too many have actually done it yet. Some say they're intimidated. So I'm happy to offer mentorship, just kind of stand by while you work the telescope and, until you get the hang of it. We have a training video and we have a user guide and everything. So our next online viewing session is on December 4th with a cloud date of December 5th. This time we will start an hour earlier at 8:30, so a little more convenient, and we should be able to get going right away. I should be able to focus a lot quicker and be ready a lot sooner, so things go a little smoother than they did tonight, but hopefully it wasn't too bad. If you're not a KAS member, you can join the online viewing session email list, because if you're a member, you'll get plenty of other reminders anyway. And of course, if you sign up to our email list, you get reminders about the sessions, registration and YouTube links, links to download the images from tonight, for example. And I can also notify you of postponements or cancellations, because we haven't canceled one yet, but we have postponed because usually of the wind, not necessarily of clouds, but sometimes the wind's too high and we have to postpone. So you can either use our contact form or email us to join the OVS email list. You'll receive like roughly half a dozen emails a year. That's all. If you are an astrophotographer, you're welcome to join us for our next Astrophoto SIG meeting. We're going to do something a little bit different. We're going to do great gifts for the astrophotographer. We're hoping to have like maybe a dozen objects that would make great gifts for the holiday season for the sky shooter and your family. And I'm looking, for members to, suggest gifts and, give brief presentations about them during the meeting. Nothing too heavy. I will make I will make all the slides. You just got to tell me what to make slides of, and you can spend a few minutes talking about your holiday suggestion. Our next general meeting is on Friday, December 5th or December 3rd. We are still on Zoom, unfortunately, and will be for at least the next 3 months after December. And we're doing something called Astronomy Open House, where at least 2 or 3 members give short, like TED-like talks. One member is going to talk about electronic assisted viewing, kind of what we were doing tonight. And another member is going to talk about his trip to Mauna Kea, where he saw, the Keck telescopes and stuff like that. The Introduction to Amateur Astronomy series will return on January 15th. You can register on our website right now. This is a 5-part series that tackles everything from reading star charts and looking for constellations to binoculars and telescopes and accessories and astrophotography. So we're looking to make this a big deal like it was earlier this year, or as it turned into. So I hope you can join us for the lecture series, either again or for the first time. And finally, here is the link to download tonight's images.